Hi everybody, Mrs. Pesic here.
And Miss Bella here.
And we are looking now at section 9.4, which is geometric sequences and series. And the objectives in this section are to find the terms of a geometric sequence, including geometric means, and to find the sum of geometric series. So our vocabulary: geometric sequence, geometric mean, geometric series. In a geometric sequence, the ratio of successive terms is a constant called the common ratio. So let's compare that to, or I should say contrast that to an arithmetic sequence where it's a common difference. This time it's going to be a common ratio. So in this case, the ratios, if we're looking at this sequence, the first term is 128, second term is 64, third term is 32, and so on. If we notice, if we take this term and divide it by the first term, 64 divided by 128 is 1/2. If we take this term divided by this term, we also get 1/2. If we take 16 over 32, we also get 1/2. So they do not have a common difference, but they do have a common ratio, and that makes this a geometric sequence. So recall that exponential functions have a common ratio. When you graph the ordered pairs, that would be n comma a sub n, so the term number versus the actual term of the geometric sequence. The points are not going to lie on a line like in an arithmetic sequence. They're going to lie on an exponential curve as shown. Thus, you can think of a geometric sequence as an exponential function with sequential natural numbers as the domain. You want to add anything to that?
So remember, our domain is our x value. So if you this picture is kind of an example of it. Talks about players in each round at Wimbledon. So if it was round 1, the number of players, this is actually going to be about 128 players. But in round 2, now it's decreased exponentially. So in round 2 now there's only 64 players. So we're going to see that it's a curve. Whereas if this was something that was arithmetic, you would see just a nice line with a constant slope that it was going up as changed over time.
Or a line with a negative slope.
Right. Either way, increasing or decreasing.
Okay, so let's take a look at this first example. We are trying to determine whether the sequence could be geometric or arithmetic. If possible, find the common ratio or the common difference. So let's test this first one. Let's see if it's got a common difference. If we do 100 minus 93, no, 93 minus 100, that's a -7. 86 minus 93 is also a -7. 79 minus 86 is also a -7. Sure looks like it is an arithmetic sequence because it has a common difference, and the common difference here would be -7. If we take a look at this next one, does this have a common difference? If I do 90 minus 180, that's a -90. If I do 60 minus 90, that's only a -30. This is not going well for a common difference, so it's not an arithmetic sequence. Let's test it to see if it is a geometric sequence. We know it's not arithmetic. So to test it for a geometric sequence, we're going to want to take the ratios. So if we take 90 divided by 180, we end up getting 1/2. And if I take 60 divided by 90, when I reduce that, I get 6 over 9, which is 2/3. Well, 1/2 is not equal to 2/3, so they do not have a common ratio either, which means this is also not a geometric sequence. So that means we would say this one is neither. All right, and then let's take a look at this example. We have 5, 1, 0.2, and 0.04. If I try and do common difference, 1 minus 5 is a -4, but 0.2 minus 1 is like a -0.8. -0.8. Well, that's not equal to each other, so it's not arithmetic. There's no common difference. So let's test it for to see whether it's geometric. So this time, if we take the ratios, if I take 1 divided by 5, I'm wondering, is that the same as 0.2 divided by 1? And is that the same as 0.04 divided by 0.2? And if we want to test this with our calculator, if we do 1 divided by 5, we get 0.2. If we do 0.2 divided by 1, we also get 0.2. And if we take 0.04 divided by 0.2, we also get 0.2. So the ratios were the same each time. So we would say that since these are all equal to 0.2, we would say that it is a geometric sequence. And we would say that the common ratio, we're not going to use D because that's for the common difference. We're going to use an R for common ratio. The common ratio is 0.2 for this example.
All right, this leads you to your first must-do. So you're going to determine whether the sequence could be geometric or arithmetic. If possible, find the common ratio or difference. So again, start by subtracting, see if that works. If so, tell us what the difference is. If not, try the division, do the ratio, tell us what the common ratio R is. If not, then it could be classified as neither. Now, when we are dealing with geometric sequence, each term is going to be classified as the product of the previous term and the common ratio. So, you know, we would be multiplying by the same thing, but you need to know what number you're starting at so you know what to multiply by. So this gives us a recursive rule, which means it refers to the one before it. So our recursive rule for a geometric sequence is a sub n is equal to, so your nth term, you take a sub n minus 1, which is the previous term, and you multiply it by the common ratio. So, I mean, this is helpful if you have your terms in order, but what if you have, you know, only term 1 and 2, and I want to know term 12 or something? You don't want to actually find all of those in between. So we also can use an explicit rule. Again, that means it does not rely on anything else. And we're going to use this to find the nth term instead of a geometric sequence. So each term is the product of the first term and a power of the common ratio as shown in the table. So for example, this goes back to that chart we were talking about Wimbledon in the graph there. So in the first round there were 128 powers. So instead of, you know, using this recursive formula again, we're going to take our common difference, or common ratio, excuse me, so 128 to 64, again, you get that by multiplying a half, and 64 to 32, that's a half. This 1/2 is the common ratio between these. So we're going to say that that is really 128 times 1/2 to the power of 0. When I get 64 in round 2, that's 128 times 1/2 to the power of 1, and so on. In round 3, it's to the power of 2, 3, and then in general, you see that it's kind of raised to the power of 1 less than whatever round we are on. So this is going to develop for us what the formula will be. So generalizing it, when I want to find what the nth term is in a geometric sequence, I'm going to use this formula here. I'm going to say that a sub n, so whatever term I'm looking for, is equal to a sub 1. Again, we know that that is the first term, multiplied by r raised to the power of n minus 1. Again, r will stand for my common ratio. So what are you multiplying terms by to get from one to the next? So let's use that pattern and help us find the 7th term of the geometric sequence. So I'm starting off with 3, 12, 48, 192. Again, my pattern or my rule here will be a sub n is equal to a sub 1 multiplied by r raised to the power of n minus 1. So my first step is I want to find the common ratio. Again, you already know it's geometric, so I'm going to start off by taking 12 divided by 3, so the second term over the first. That should be the same as 48 divided by 12, which should be the same as 192 divided by 48. Every single one of these reduces to 4, so my common ratio is equal to 4. So I know one more step of my pattern here, or my value, that r in this case, my common ratio is equal to 4, and also we were already given our first value, our first term, a sub 1 is equal to 3. So the rule that I'm going to use in order to evaluate this is going to look something like this. In order to find the 7th term that I'm looking for, so a sub 7, this will equal a sub 1, my first term, which we said is 3, multiplied by my ratio, which is 4, raised to the power of n minus 1. Again, n, this takes whatever term you're looking for, and I'm looking for the 7th term, so the power of 7 minus 1. Now, order of operations, I'm going to do my exponents first. So this is really 3 multiplied by 4 raised to the power of 6. Again, I should do my exponents. So 4 to the 6th, if I take that value and multiply it by 3, we're going to end up that the 7th term is equal to 12,288. So again, this is helpful. Instead of finding all the terms in between, I can skip right from the first 4 that I had all the way down to the 7th term.
All right, let's take a look at this example. We're going to find the ninth term of this geometric sequence. We're starting with 3/4, -3/8, 3/16, -3/32, and so on. Well, we first need to find our common ratio. They told us it's a geometric sequence, so -3/8 divided by 3/4 should be our common ratio, and it should be equal to 3/16 divided by a -3/8, and so on. Let's use our calculator to get this common ratio. If we do -3/8 divided by -3/4, let's see, -3/8, and I want to divide that by the 3/4. Oops. And when I do that, I end up getting -0.5. And if I could test it with the next one, if I do 3/16, and I want to divide that by -3/8, and when I do that, I end up getting -0.5 again. So it looks like they're all going to be equal to -0.5, so that's going to be our common ratio. All right, and so that means that our sequence formula is going to be a sub n equaling a sub 1 times r to the n minus 1. So that's going to be a sub n equaling, our first term was 3/4. We saw that right here. And now we need our common ratio, which is -0.5 raised to the n minus 1. So that's the formula that we want to use, but we're asked to find the ninth term. So we're going to say a sub 9 is equal to 3/4 times -0.5 to the 9 minus 1. So a sub 9 equals 3/4 times -0.5 to the 8th. And when you work that out on your calculator, it turns out that the -0.5 to the 8th is really 1/256. And we multiply that by 3/4, and we end up getting 3/1024. And if you got a decimal for that, that's okay too. That's a 0.00293. All right, that brings up your second notes must do. We'd like you to find the ninth term of this geometric sequence. So remember to find your common ratio first by dividing, second term divided by first term and so on. And then you're going to use that formula that we talked about. That's that a sub n equaling a sub 1 times r to the n minus 1 formula.
Okay, example 3 here. We want to find the nth term given two terms. So I want to find the nth term of the geometric sequence, and I'm given with the third term, a sub 3 is 36, and the fifth term, a sub 5 is 324. So my first step is to find the common ratio. So normally when I would find the common ratio, what I would do in this case is I would just divide the two numbers, and that would be my common ratio. However, in this case, I'm only given the third term and the fifth term. So I am going to still start off by doing the same thing, and I'm going to still divide them. So I'm going to find out that my ratio between the two of these is going to, kind of be derived from the two of those. But let's use our formula just so we are clear on what we're going to do here. So our formula is a sub n is equal to usually a sub 1 times r raised to the power of n minus 1. However, in this case, I don't have my ratio. I don't have my first term. So we can actually adjust this formula a little bit to help fit what I have. So instead of having a 1 here and a 1 here, I can really plug in any term that I'm working with and sub that in. So I'm going to say instead of using the first term, the first one that I have is the third term. So I'll say a sub 3, and then in my formula I'll say n minus 3, and that will kind of help me adjust a little bit for whatever I'm working with. So now I can use the fifth term, which I know was given to me. So I'm going to use that in the new formula. I adjust a little bit, and that's going to help me solve for what that ratio is.
N is going to be 5 in this case?
So n is going to be 5. So I'm going to use this again for my fifth term, so n is 5. So a sub 5, so my fifth term was 324. That is going to equal my third term, which was given to me as 36, multiplied by r raised to the power, again, n is 5, of 5 minus 3. So if I want to know what is my value of my r here, well, order of operations says that the first thing I should really do here is deal with my exponents. This is really 324 is equal to 36 times r to the second. In order to solve for r, I would divide both sides by 36. I'm going to end up with 9 is equal to r squared. And we know from Algebra 2 how we get rid of a power of 2. I'm going to square root both sides. But I need to remember I need two answers to account for from this. I'm going to have a plus and a minus the square root of 9. So my r value is actually going to equal plus or minus 3. Okay, so I'm going to have two different ratios that could have gotten me there. So when I do this, I need to have a little caution here. Because when we are given two terms of a sequence, you always want to make sure that if you had a positive and a negative value, you consider both of those for r. So when we go about finding out what our first term is, a sub 1, I'm going to need to consider both possibilities here.
But that's if you were taking like a square root of both sides or a fourth root of both sides. But if it was like a cubed root, you wouldn't have to worry about that.
Remember, those don't have a plus or minus outside the radical. Okay, this one did though, so let's see what we're going to do. So let's do two cases. So case 1, we're going to treat it as if r was equal to positive 3, and then we'll come back and we'll do case 2 as where r is equal to negative 3. So starting off with r is equal to 3. Again, my goal, if I wanted to find the 8th term, well, I'm going to need in this case what the first term is. So in order to find the first term, I'm going to go back to my original equation here, which, you know, we were given up here. I like to highlight things. So this one right here, and we're going to plug in what we know. So a sub n, we know our third term in this case was equal to 36. So I'm going to use that same formula, and I'm going to be using, in this case, 3 for my common ratio because I already found that to be true. So if I use this for a value that I know, which was, again, the third term was equal to 36, I'll say that the third term, or 36, is equal to the first term, which I don't know yet, multiplied by 3 times n, which is my third term, minus 1. So in this case, I'm going to have 36 is equal to a sub 1 multiplied by 3 to the second, or, whoop, that's what happened when you use the highlighter there.
That's usually my job.
That is, I usually change it over and forget to switch it for you. A sub 1 times 9, and if I divide by 9 here and divide by 9 here, one case is when r was positive 3, my first term could have been a positive 4, and that's from 36 divided by 9. Now, case 2, what if instead of my ratio being positive 3, my ratio is actually negative 3? Well, using that same formula, we'll say that this time I would have a negative 3 raised to the power of n minus 1. So again, let's use that information. We know that the third term actually is 36. So the third term, or 36, is equal to the first term multiplied by negative 3 to the 3 minus 1, because I use the third term there. So 36 is equal to a sub 1 multiplied by negative 3 to the second. Since I'm raising that whole thing to the second, is actually going to still square it and make it a positive 9. So 36 is equal to a sub 1 multiplied by positive 9, and when I divide both sides by that, it just so happens, again, in this case, my beginning term is still going to be positive 4. So no matter which ratio you use, this sequence must have started at 4.
But we're also trying to find a sub 8.
All right, so one final step. This was kind of a long one, but had a lot of good stuff happening in here. So we had two rules that we created. One rule was a sub n was equal to 4 multiplied by 3 raised to the n minus 1 power. The other one we did was that a sub n was equal to 4 multiplied by negative 3 raised to the n minus 1 power. So for each of these to find the 8th term, let's see what that would give me. So the 8th term here is equal to 4 times 3 raised to the power of 8 minus 1, or 4 times 3 raised to the 7th, or this value would be equal to 8,748. Okay, that's one option for the 8th term. Using our other rule, a sub 8 would equal 4 multiplied by negative 3 raised to the power of 8 minus 1, or 4 multiplied by negative 3 raised to the power of 7, and this is going to give you negative 8,748. So depending on what that ratio is, your 8th term could have either have been a positive or it could have been a negative, depending on which one we used.
So can we just take a look at this sequence? This sequence started off, we said the first term was equal to 4. So if the common ratio was positive 3. Then we'd be multiplied by 3, we'd get to 12. 12 times 3 is 36. 36 times 3 is 108. And then the fifth term, which we already know is, what was it, 324?
Yeah.
Right? And so on. And we would get eventually to the eighth term, which was 8,748. That's if our common ratio was equal to positive 3. If the common ratio was equal to negative 3, what's going to be different about these two is that we would still start with 4, but then 4 times a negative 3 would be a negative 12. Then negative 12 times the negative 3 would be back to a positive 36. The positive 36 times the negative 3 would give us a negative 108. And then we'd get to the positive 324 that we were told was going to be the fifth term, and so on. But when we keep oscillating between positive, negative, when we get to the eighth term, it would be a negative 8,748. Okay, so this brings up your third notes must do. Find the seventh term of the geometric sequence with the given terms. A sub 4 equals negative 8, and A sub 5 equals negative 40. Any tips you want to give them on that one, Ms. Bell?
So remember, maybe use your general formula that you're going to use here. So A sub n is equal to A sub 1 multiplied by r to the n minus 1. So slightly adjust just a little bit. Well, actually, you don't need to adjust this one because they're only one apart. So why don't you do A sub 5 over A sub 4, whatever that is, that will be your ratio right away. So yeah, those are consecutives, and there's many fewer, less steps for you to do on your own here. So that's kind of a nicer one for you to do.
Okay, so that brings us to geometric means. Geometric means are the terms between any two non-consecutive terms of a geometric sequence. So if A and B are positive terms of a geometric sequence with exactly one term between them, then the geometric mean is given by the following expression, square root of A times B. And I hope you remember from geometry, learning about geometric means, those showed up in those right triangle problems. This is example 4, so find the geometric mean of 4/9 and 25 over 36. So the geometric mean here would be square root of 4/9 times 25 over 36. And so that gives us square root of, when we work this out, we end up getting square root of 25 over 81 when we reduce things. And square root of 25 over 81 is 5/9. And if you remember from geometry, the way we would set this up is we would say, what is the geometric mean between 4/9 and 25 over 36? So we would set up x as the geometric mean, and it would go here and here in our proportion.
The indicated sum of the terms of a geometric sequence is called a geometric series. So again, it's listing all of those but now adding them together. So you can derive a formula for the partial sum of a geometric series by subtracting the product of S sub n and r from S sub n as shown. So again, yeah, we didn't show that, but we're just going to jump to the formula for you. But just notice it says partial sum. Remember, these go on forever. So it says partial sum because you're only going to add the first however many to figure out what this is. So our formula for geometric is going to be S sub n is equal to A sub 1. So again, that means you're going to have your first term in here, okay, multiplied by, and you have a fraction here. So in the numerator, it is 1 minus r to the n, where r is your ratio and n is the number of terms you're adding. And in the denominator, you have 1 minus r, so again, that r is a common ratio. So we're going to use that formula to find out what the sum of these first 8 of this geometric series is equal to. So again, just for reference, because it's on the other page, the formula here for S sub n, so for the first n terms, is going to be the first term, A sub 1, multiplied by 1 minus the ratio to the power of n divided by 1 minus the ratio. So there's what we're trying to fill in. So the first thing I need to know is, what is my value of r? Again, my A sub 1, I already know. It's my first term here. So that is 1. That's given to me. So the only other thing I need is the r value. So our first step will be to find that. So to find your ratio, I take the second term divided by the first term. That should equal the third over the second and the fourth over the third, and so on. Hopefully you agree that all of these are equal to 2. So my common ratio is equal to 2. which is kind of summarized here in step 2 for you. The first term was 1, the ratio we just found is 2, and we were asked to find the indicated sum, or S sub 8. So I'm looking for 8 terms added together. So my pattern here, my formula is going to be S sub 8. So the sum of the first 8 terms is equal to A sub 1. Oh, too far. All right, A sub 1. So the first term, 1 multiplied by 1 minus my ratio, 2, to the power of n, so 2 to the 8th, over 1 minus 2. Okay, so to clean this up a little bit, a factor of 1 out front, 1 times something is not going to change its value. So we can say that the sum of the first 8 terms is really equal to 1 minus 2 to the 8th. Well, 2 to the 8th is 256. And in the denominator, 1 minus 2 is negative 1. So if I want to simplify this, 1 minus 256 is really negative 255. And if I divide that by negative 1, it's telling me that the sum of the first 8 terms is equal to 255. Okay. All right, and that ends our notes for 9.4. So thanks for watching.
And have a good day.